DeepSeek has been all the hype, and today we want to build a real-world product with it, specifically a RAG chatbot that allows us to chat with our documents with everything running fully on our devices. For that, we will use DeepSeek's R1 reasoning model, an open source vector database called FAISS, Streamlit to build a web application, and LangChain to put everything together. So let's get started. DeepSeek has been all over the news recently, and it sparked major discussions in the entire AI industry. It even cost a few companies quite a substantial amount of money. But today we want to focus on the open source aspect of it and run it locally on our devices. The RAG chatbot that we're building allows us to chat with our documents, and in our case we will use markdown files, but this also applies to any other file format that we think of, for example text files, PDFs and more. So it's really a tool that you can use for many use cases. The tech that we're using is going to be DeepSeek's R1 reasoning model, and we'll combine it with a vector database that is open source and maintained by Meta that is called FAISS. To build up a front end, we will use another open source tool called Streamlit that allows us to build up front ends using Python. To tie this all together, we will use LangChain because it has just great tooling support that allows us to build things very quickly. Again, I want to emphasize that with this tool, we can inject knowledge into conversations with an AI very easily. If you want to see the full code for the project, check the link in the description. And for now, let's get started with the project setup. If you want to see the full code of the project, check the link in the description and the full video to see an entire walkthrough of how we create the project. Follow for more content like this. We want to have a clean project setup, so we jump into a new folder that is empty at the moment. And first of all, we create a new Python virtual environment. We call it venv. And to activate this, we call source venv bin activate if we are on macOS and Linux. If we are on Windows, we can leave out the source part. We see that it's active with the sign here on the left. And so the next thing that we do is we install the dependencies. These are quite a few, and while this runs, let's quickly just mention that this creates an isolated Python environment where only these packages are installed. It makes sense to do this because we have a clean setup that uses only these packages in their specific versions that are relevant to this project, and we don't interfere with any of the globally installed packages. So it's highly recommended to use an approach like this. There are other tools to do it. We just use the venv one here. Now this has finished running and we're good to go, but another possibility to do this is that we can install packages from a requirements.txt file. And if you take a look at the repository, again, it's linked below in the description, we can take this file, save it here, and load all the required dependencies from this using the pip install -r command. So feel free to take either approach, but for now we have set up all the dependencies we need for the project. So let's jump to the next chapter. Next up, we want to run the model locally on our devices. So for that, we have different options. There are a lot of tools out there, and I'll link a video that discusses some of the most popular ones. But today we are going with the tool called LMStudio. So let's take a look at how we can download this to our machine. I'm in the browser here, and this is how you can use it. You go to lmstudio.ai, and then we can download the tool for the Mac, for Windows, and for Linux. You can just click the download link and install it. And once that's done, we can see it looks like this. It opens up with this interface here. We have a chat, developer, models, and discover option. Let's go with the discover one for now, because here we can search for DeepSeek R1. And here I selected best match, and we can see we have different options here. We have the R1 distill with the Qwen 7B, and there are quite some options here. And if we go over them, we see the size here. For example, this is an 8 billion model. This is a 7 billion model. And we also see the amount of downloads. And we can also see that for the bigger models that have larger memory footprint, we see that this is likely too large for this machine. So we can go with a smaller model, for example, this one, and click on the download button to download them. Then they will show up in the My Model section. And for example, here I have the DeepSeek R1 Distill Qwen 14 billion parameter model that comes in at roughly 9 gigabytes. Here, feel free to select smaller ones. This is just the one we're going with. Now, to make this available to our application, we need to switch to the developer section. And then here we can select a model to load. And now I want to use the DeepSeek R1. I can select certain options here that we will leave like this for now. And I can hit load model. Now, it will take a while to load, but the good thing is if I say I want to make this running, I have this model available at this URL. So I can go to HTTP 127.0.0.1 on port 1234. And now I see that the server has started. I can interact with this model using the OpenAI-like endpoints. So for example, with the V1 chat or V1 completions, I can access this. And this is exactly what we will do in the next step. But I want to emphasize again that this is just an example for a tool. We can go with other options as well. It's just important to know that the address and the port are important to know which endpoint we need to hit later on when we write the code for it. But for now, it's just important for us to know that the model is running. We can access it so we can continue with the next section. Next up, we need to create a vector database. I don't want to go into too much detail, but just to give you a quick impression of what a vector database really is. The format of a vector database is different compared to regular databases such as SQLite, which will store values in a table, but instead values are stored in a multidimensional space and vectors just represent a certain point in that space. And the advantage we get here is that similar information will be stored in a similar position inside of the space. So with that comes the ability to compare information or text by its similarity. So if the information that is stored inside of a text is similar, it will be closer inside of this multidimensional space. And if the information is different, the distance will be further apart. So it's easy for us to find similar information in the database that we're looking for. We have, again, a ton of options, but since we want to go with open source tech, we go with the option of FAISS or FAISS. I'm not sure how to pronounce it, but it's an open source database by Meta. You can see the GitHub repo there. You can take a look at the code. We have different options to use it. For us, we will go with the option that LangChain gives us. So they have a vector stores package. We can combine the embeddings from Hugging Face with the vector store FAISS, and we can use the LangChain community package for that, and this makes it really easy for us. I didn't talk about embeddings yet, but embeddings are just a model again that represents knowledge about words and the world. So it gives us help when we want to store the data inside of the vector database to basically find out where to store it. And there are multiple examples that you can use. See here, there are many different ones. And again, for the database, there are also many options. We just go with this combination. So for that, let's open up our project in VS Code. And we'll start off by creating a new file here. And we'll call it create vector store.py. And we open up the file. we close the sidebar and let's start coding this up. First, we need to think what we need to do to create our vector store. And the first step we need to do is to load the text that we have inside the files. So let's create a function and call it load text from docs. And I will show you the documentation in a second, but we know that it contains of markdown files. And we first need to specify where the docs are located. So let's define the root here. In our case, we will take the iOS documentation that is located in the root folder here. And we will go recursively over all the files inside. We go with the file types of Markdown and MDX. And then we need to import the OS as well as the iglob packages. And with them, we can iterate over all the files inside these directories. So we will go recursively over all of them and say if this is a file, we append this to the array of files. And then we can filter them to have the correct extensions here. So we split them by the dot and take the ending and compare them to the file types. So we have all the Markdown or MDX files filtered out. And then we want to have text elements that we can later store in the vector database. So let's define the array for now. And then we go over all of these filtered files. And for each of them, we will use an unstructured markdown loader. So we will load for each file the markdown content inside of the loader now and call the load function to get the data. We can print out how many documents we have in there, which is just information for us to log. And then we want to split this. And for this, we can use another tool, which is called the recursive character text splitter, which comes with a few interesting parameters. So we initialize this here and we can define a chunk size. So this is the size of each text element that we get. And it's 1000 characters. And then we have a chunk overlap. So we split information here at a certain point, and it might be the fact that certain information gets lost because we split inside of a sentence. For that, we overlap each of the chunks by 200 characters to make sure we capture the information that is towards the split directly in either of the chunks, either the first one or the second one in this case. Then we use the text splitter to split the data that we just loaded. And for all splits, we simply append the doc, so the content of the split that we just created, to the text elements here. And in the end, we return the text elements array. So with that, we have created an array of all the text elements from the entirety of the docs that we have analyzed. And this is just the example here. We can put anything in there. It's just an example of what we want to take here. So the next step is to put this data into the database. For that, we take the text chunks, so the text elements that we just defined, and we also take embeddings. And I already mentioned that embeddings is just a vector representation, and this helps us to characterize where to store the actual chunks inside of our database. We need to import the database. So we take from the community package, the vector stores, the FAISS package, and we can now initialize this from the texts with the text chunks and the embeddings. So it's a one-liner, which is quite fascinating. So it's very easy to put this inside of the database. We also want to save this because we don't always want to do the same work again, but it's fine for us to do this once, and whenever the data changes, we can rerun this. But if we're done here, we save this in a local database with the name of FAISS index. So we can later load this. And then we return the vector store. We have the functions ready, but now we want to create the actual vector store by either loading or creating it. And for that, we first take the Hugging Face embeddings that we just mentioned. We import them and then we initialize them with the model name. And now we can try to load them from this local path. Again, that's the same we defined here. So whenever we have already stored the data inside the database, this will hit, and the vector store will be initialized with the embeddings, and then we can return it. If that fails, we know the vector store has not been there yet, or something else went wrong. Then we first load the text from the docs. So we take the text chunks, we create a new vector store, and with that save it locally, and then return that vector store. So we can call this whenever we need it, which will be in the next step. And the vector database will be initialized or loaded from the disk. Either way, we will have a vector database to work with, and we can continue with creating the actual chatbot next. In order to build our chatbot, we will use a tool called LangGraph, which is part of the LangChain ecosystem. And it's basically a tool to build up a graph of different agents and nodes that know how to interact with each other to achieve a certain goal. For us, this will look very simple. And just to get you a quick idea is we build up our graph, and this graph consists of a starting node, and then we can add nodes with all the functionality that we want. So for us, that will be a retrieve node as well as a generate node. The retrieve node will take care of getting to know the information from the vector database, and the generate node will take care of generating an answer with that knowledge. In the end, we will see the result that we get from the LLM, and we can show this to the end user. So without further ado, let's jump back into VS Code and create a new file here that we call RAG Chatbot. It's a Python file again. And the first thing we need to do is define a state of our graph, which can be manipulated by each node, but we want to have the basic definition of the data we need here. So let's define this state. We will use a typed dict from the typing extensions package. And inside of that state, we want to first have the question that the user sends to the chatbot. Then we will have a list of documents, which will be the context. So this is the list of information that the system retrieves from our vector store. And then finally we have the answer. That's what the LLM will output. Then we define our first node, the retrieve node, which takes in the state. And first it will create a vector store and load it. So either it will load it from disk or it will create a new one. We perform a similarity search on the vector store with the question that we get inside of the state. And we will retrieve some documents back, these which have the highest similarity score to the question itself. And then we will simply return this as the context, and we put in the retrieved documents as the context. You can see the type here, so type list document, which is exactly the type that we defined before. Then we will also define a generate node, which again takes in the state. For that, we will use the chat-openAI object, which we will define like this. And this gives us the option to define a base URL, which is the same as the path to our LLM that we are running inside LMStudio. So if you remember this was the URL that we exposed our endpoint with. So this is where the DeepSeek R1 model is currently running, and we set the streaming option to be true. With this, we already have the LLM ready. Then we need to import the hub because we will pull a basic RAG prompt from it. We could also define it ourselves, but let's reuse this one as we know it's a well-working prompt. And then we take the content of the docs, where we simply take all of the document elements in the list and we simply join it as a string with new line elements between them. So this is a long string of the document's content that we have. And then we use the prompt to invoke with a current question, which is inside of our state, as well as the context that we also extracted from the state. And we store that inside the messages object. And finally, we invoke the LLM with these messages to generate a response. And we will return this response in the state object's answer property as a string object. With that, we can now create our chatbot, which will put everything together. So we first need to import from LangGraph the state graph object, as well as a start property, which we will see in a second what that means. We will use the state graph object that we just imported and initialize it with the state property that we defined. And then we add a sequence, which means this is the steps that we allow the agent to perform. And for that, we have the retrieve method as well as the generate method. So the graph can now go over these steps and combine them to generate an answer. We add an edge, which is the start edge, which will be connected to the retrieve action. And then in the end, we compile the graph to receive the outcome that we need, which is a compiled state graph, and we return this graph in the end. With that, our RAG chatbot is already put together and functional, but we still need a way to call it, and that's where the next chapter comes in. The last step in making our app actually usable is to, well, create an app out of it. And for that, we will use Streamlit, which is a Python tool that turns data scripts into shareable web apps in minutes. So we'll try that. They have excellent documentation, and it's great to build upon the tooling that we actually used so far. So let's jump into VS Code, and we create two files. First, a app.py that we will fill with the logic for the app itself. And then we will also create an HTML templates.py that we will use to add some custom styling to our application. And for that, we will just magically fill that with content, because I don't want to go into too much detail here. It's basically just some CSS styling for different classes that we will reuse inside of our app. So let's jump back to the app file and close the sidebar. And we'll start off by adding these HTML templates that we defined before to the file. I'll explain how they work when we need them. And second, we import Streamlit as st here to be able to use this inside of the app. Then we start by saying if we are in the main execution file here, we first set a page config with the title chat with stream docs and a boat icon as the page icon. This will be inside the browser. So we'll see that then to set some basic properties of the page. And then we will write the CSS that we have defined inside the HTML templates to apply to this page. Next, we will create a header. So it's quite convenient that most of the components that we need can actually be used from the Streamlit SDK. So a header will simply be a title for the web page. And then we say if the chatbot property is not inside of our session state. So the session state is a property that contains all the necessary state we need to have in our app. So we can say if it's not there, we show a spinner. So we'll show a loading spinner that says loading data, and we import our chatbot and we define the chatbot inside of our session state and assign the chatbot property with the chatbot that we are creating. So how this works is that initially this will run. It will create the page config, it will write the CSS, it will create the header, and then it will check for is the chatbot property there inside the session state. If not, it will jump in here, say, okay, we're loading data, so it will hold execution here and assign the chatbot after it's loaded to the session state, triggering a reloading of the page. All this code is executed again, and this property will no longer be true, so we will no longer jump inside here, but already have the chatbot inside of the session state. We do another check if we have chat history inside the session state. If that's not the case, we just set it at least so that we have an element here. And then we show a text input element that says, ask a question to our documentation. We will assign this property to the question variable. And then we say, if we have a question variable, so basically the user will input text, and upon inputting this text, it will be assigned to question. It will trigger again a check of this script, and it will now say, okay, we have a question now. So we show a spinner again, just like we did before, which will say thinking. And it will then call the handle question function that we haven't defined yet. And upon finishing this, it will execute this whole script again. So let's define the handle question function now. And for that, we say we want to have the chatbot that we have inside of our session state, which is a global variable that we can access. We invoke the chatbot with that question. If we just quickly check, the question property here is assigned to the state of our LangGraph object, so of our state graph, and it will assign the question property here. Next, we assign the chat history variable from the session state object, and if it's none, we set it as an array. And then we append the content of the question as defined by a user, so we will put an element into the chat history array as a user message. And then we will also add the response object we're getting from the bot, so from the chatbot, assign it with the user property of bot. And then we will assign the updated object of chat history to our session state object. Then we enumerate over the chat history in reverse order, so the latest additions come first. And we say if we have an even index, we show this as a bot message. And here the bot template comes into play. So let's quickly take a look at the bot template that we defined inside HTML templates. Here we have a div of a class chat message. It will have a title that says documentation bot. And here this syntax allows us to inject a message into that template. And this is exactly what we're doing here. We're writing the bot template and replacing the message object with the content of the actual bot message. If we have an uneven index, we write this as a user template. And to quickly go over that again, we have the same thing. We simply have the user message CSS class attached here. Aside from that, we also have the message property that we will replace inside the user template with the user's message. And with that, we have a working app that we can now test and see if everything works just as we expected. To run the app, we have two options. The first one is we can open up a terminal and we can type in Streamlit run app.py, which will run the app from the terminal. But what we can also do is define a launch.json file inside of our VS Code folder. And if we take a look at this, we can say we want to launch Streamlit here with the Streamlit command saying run with the current file, and we define a server port of 2000. And what this allows us to do, if we click on the run and debug option here, we can now, inside this dropdown, select Python Streamlit app. And if we do function F5, we can run our application and it will launch. And if we jump back to the browser and we go to localhost 2000, we will see it is working. But before we actually run a query, we need to add the necessary data to be parsed. So let me quickly grab that and drop this here. So we copy over the folder. And now inside of this iOS folder, we have the markdown files. So for example, we have an installation guide on the stream video docs in that case. But like I said, this can be anything that you want. So here, for example, you get to know how to install the SDK and more. So let's jump back into our browser again and let's ask it the question, how can I install the Stream Video SDK for Swift UI? And it will think for a while. So it will now trigger the process of running the agent, and we can already see the logs inside LMStudio give us that, hey, we're running this application, we're streaming a response, we generated the first token and continuing to stream the response. So it seems to be working. We see it's generating a response. So if we switch back to the browser, we will now see the response popping up soon. And remember that we downloaded a rather large model, so it's quite to be expected that the generation will take a while. If we have a more beefy machine or a smaller model, it will of course run faster. So it will show us the user question here. It will give us the answer. We see the bot is thinking. It says, okay, the context mentions the Swift package manager. That's correct. So it gives me an installation instruction. Okay, to install it, open Xcode, go to File, add packages. Nice, that looks good. So let's add another question here saying, how can I join a call with a code example? It will think again, so I will speed this up now to see the response. And we see the response. It again thinks for a while and checks the examples, and it will then give me a code example to join a call in Swift, create a call instance with the desired type and ID, and then call the .join method. Here's an example. Let call, result, try await, call.join. So everything works as expected. Awesome. The project is done. We have seen it in action and it works quite nice. So to sum up what we have achieved here, we have used completely open source technology to build up a Agentic RAG Chatbot using DeepSeek's R1 model that is a reasoning model, which might not be a perfect fit for a chat use case like this. But the good thing is that using LMStudio, we can replace this model using any other chat model that we like by simply loading that different model, and it will then be exposed via the URL that we have used. So it's quite easy to replace the model if we want to use another one. Also, we have used the model to chat with the documentation of the Stream Video SDK, but we can use any other documentation or files that we want. We just need to ensure that it's either markdown format or that we change the code to load these files depending on the file format. We've also used an open source vector database in FAISS that we can replace with any other one that we might want. So I think we've built quite a robust solution using the LangChain ecosystem and LangGraph specifically to build an Agentic RAG system. Again, if you're interested in seeing the entire code for the project, check the link in the description to the GitHub repo. If you want to see other projects being built or other tech being used, then let us know in the comments and we will try our best to build these. But for now, thanks for watching. Feel free to like the video and subscribe to the channel, and see you in the next one. Bye.